Okay, so welcome back from the weekend. So last week we kind of introduced compounds and we kind of went through a basic lesson on the basics of compounds. Well, this week we're going to kind of go through one type of compound, which are called our ionic compounds. And they're formed by ions. Okay? And so ions, this should be a term that we are a little bit familiar with. So these are the simpler compounds. Most of the world is not ionic compounds. Most of the world is the other type that we're going to talk about, covalent. So we're going to start with kind of the easier, more simple compounds, which are called ionic. Now, just a reminder, and this is going to come up a number of times, it's really important to remember that when you're going to make an ionic compound, you're going to combine a metal element and a non-metal element. They're going to come together. So an example, the classic example is sodium chloride. So here we got chloride, which is the non-metal, and then we got sodium, which is the metal. Okay, and they're all bonded together. All right. So just going to do a quick recap from last week. So elements form compounds to be reactively neutral. Okay, all elements except for the noble gases are reactive. So they're all trying to basically form a compound. Since they form a compound, they become way less reactive. Now they are, so we call that reactively neutral. Now they were already electrically neutral. And what we mean by that is they have the same number of protons and electrons, except for if you have an ion and you've lost or gained some electrons. Okay, the next one, in order for a compound to form, if you're going to form a compound, electrons must leave one atom and either permanently, like in an ionic, or temporarily in a covalent, go to another atom. So an example, if you look down here at my picture, when we're going to form sodium chloride, this electron right here in the outer ring, called the valence electron, is going to jump from there and go on to chlorine. And when that happens, we get this over here. We get sodium with a full outer ring, and we get chlorine with a full outer ring, and now that's reactively neutral. Okay? So the first compound we're going to discuss today are ionics. Now we're really only going to go through four things on ionics. Okay, we're going to go through them very basically. The first one is just ionic basics and when we use them, so why we're even studying them. The second one, we've already talked about physical and chemical properties, but we're going to talk about now ionic physical and chemical properties. We mostly went through element physical and chemical properties, but now we're going to talk about, well, once you make a compound, what are some of the abilities that it has and some of the characteristics. Then we're going to go through the formation of ionics and then the naming of ionics. So then the others. Okay, sorry, I just kind of skipped through. So just some basics. So normally an ionic forms when a metal element bonds with a non-metal element. In almost all cases, that's true. Now, this is why we start with ionics, is because they're very simple. Ionic compounds all really look similar and are either a rock, a salt, or a crystal. That's it. Right? When we get into covalent, there can be lots of different things, but ionics are not. They're very, very simple. They all are very, very similar. They're either rocks, salts, or crystals. So they're kind of things like we have over here. Okay, and that's a kind of some. There's a rock in here. That's a rock. Okay, this is what we would call a crystal down here, and this would be a salt right there. Okay, and this would just be another rock, and that would probably be another rock as well. So almost all rocks, crystals, and salts are really just ionic compounds. They're metals and nonmetals. So if you look at all these pictures up here that I've had, all of these are combinations of metal elements and nonmetal elements. They have to be. Okay. Now, something also very peculiar about ionics is they form a crystal lattice at the molecular level. Not really molecules, but rather crystals. So this is what an ionic compound looks like, okay? It's very different than, like, say, when we look like a water molecule. Okay, I'm just going to do a quick drawing of what a water molecule would look like. Like, water would be like an oxygen, and then we've got a hydrogen, and this is a molecule of water. Okay, so that's one molecule. Well, ionic compounds don't really do that. They form these little lattices where it's just a whole bunch of elements all connected together, and it's not really just distinct molecules like water would have, okay? Because water's not an ionic compound. There's no metal in there. Okay? So they just kind of form these crystal lattices, and I'll show you these pictures a little bit later on as well. Okay? So that's when I say the chemical formula represents the ratio of atoms. Okay? That's why it's basically saying you can't say that sodium chloride. So let me just rewrite sodium chloride. Okay? Sorry, sodium chloride. Okay, you can't, looking at that formula, you would assume that, oh, there's only one sodium and one chloride. But if we look over at sodium chloride, we can see that's not the case. There's really a whole bunch of chlorides and sodiums. So this formula right here really doesn't represent how many of each atom, like it does in, say, water, which would be something like H2O, implying that there's two hydrogens, one here, and then one oxygen. In an ionic compound, it's just a ratio. It's just telling you that every time you have one chlorine, you're going to have one sodium. Okay? So it's a little bit different what the chemical that means. All right, when we use them and why we even study them. So we harvest ionics, so like rocks and crystals, in order to isolate the metals inside them. And we know this process is called smelting or iron extraction. So if we kind of look over here, okay, this would be a rock, nickel 2 oxide. So this is just a close-up version of a rock. We would take this rock, and what we would try and do is remove all the oxygen. So all of these reds, we would remove out, and this is the process called smelting or ore mining. And then what we would be left with is pure nickel. Right? And we use that for, say, nickels in our coins. Now, interesting, we have a nickel mine in Sudbury, Ontario. So if you've ever been to Sudbury, Ontario, this is a picture of kind of a landmark they have in there, because they have a nickel mine where they mine a whole bunch of nickel 2 oxide, and then they harvest the metal in there and then they sell it. So almost all metals we have today are only obtained by us isolating from rocks. So if there was no humans on Earth, there wouldn't really be any metals besides gold and silver. There would really just be a whole bunch of rocks. And then we could isolate those metals, but humans are the only ones that isolate metals. Okay. Now the other thing we can sometimes use ionics for is we sometimes just take rocks and we use them as products. An example would be like granite, quartz, marble, concrete is probably one that you're most familiar with. So if you look at, say, this kitchen over here, this countertop is made out of marble. It's made out of a rock. Okay, an ionic compound. So there'd actually be metal inside this bonded to another metal. And if you're at home and you have, say, a granite or, say, a quartz or a marble countertop, take a magnet and put it up to it. And you might be surprised that your countertop's magnetic. And the reason why it's magnetic is it might have some iron in there, in particular if you have granite. Okay, we also use ionic crystals for jewelry. So if we look over kind of it here and here, okay, we can use these crystals. So like things like gems, okay, they're all ionic compounds. If you look at, say, a crystal, you don't often think, oh, there's metal inside, but there actually is. Okay, those are our crystals. And then we also have ionic salts for eating, snow melting, and water testing. And those will be kind of our salts there. We know mostly as table salt, but there's also kind of some other salts as well in season. Okay, the next thing we want to talk about is their properties. So their physical properties and their chemical properties. Now, when you have to try and think back, like, say, later on, all you have to do is really think of a rock and then start describing, well, what is a rock? Okay, so let's start describing a rock based on its physical properties. Well, one that's very, very telltale is that it is solid at room temperature. If you find something that is not solid at room temperature, like, say, water, or, say, ethanol, or, say, hydrogen peroxide, or, say, a gel, you know it's not an ionic compound, because ionic compounds have to be solid at room temperature. So every single one of them is solid at room temperature. So if you see a liquid or a gas, you know it's not an ionic compound. Okay? Now, related to that, they have very, very high melting points and boiling points. It's very difficult to get a rock or a crystal into a liquid and then eventually into a gas. So you have to use very, very high temperatures in order to do that. Now, we can do it, and that's what we do when we isolate the metals, is we melt the rocks, and we turn them into like this kind of molten material. But it takes a lot of energy to do that. They have very, very high melting points, so things like 1,000 degrees Celsius and plus. Okay, very, very hot, much warmer than the temperature you'd be able to get using materials at home. Okay. The other thing that's very, very important, and I've highlighted this in red because it's a very good differentiator, most are soluble in water, and they dissolve in water. This is the cause of erosion. So this is what causes erosion, is because rocks dissolve in water. We sometimes think that they won't because we can't see it immediately, but they do. Over time, if you put a rock inside a piece of water, it can take a long period of time, and things like waves and wind help speed up this process. But basically, the rocks will start to dissolve away in the water. If you think of like the Grand Canyon, that's what caused the Grand Canyon, was actually basically a little small stream going through and dissolving rock and getting deeper and deeper and deeper. And that's what caused the Grand Canyon. Or even our Great Lakes right now. So the Great Lakes around us, like Lake Erie or Lake Ontario, you're probably most familiar with Lake Erie. What caused Lake Erie was when the glaciers were where we are now. So there's these gigantic glaciers where we are right now. As they retreated, they started melting. And when they melted, they basically melted these giant craters into the ground, and that's what formed our Great Lakes. The other thing, most will conduct electricity when dissolved. So if you drop a rock into water and it starts dissolving, it will start to conduct electricity because it has metal in it. Now, if you take your standard rock or stone, it probably won't work, but something like sodium chloride would. Okay, so sodium chloride is, again, an ionic compound. It's a crystal instead of a rock. You drop it into water, it dissolves, and it becomes very conductive with electricity. So salt water is very, very dangerous in terms of electricity. So in particular, being in the ocean during an electrical storm is very, very dangerous. Now, the other telltale sign is that they are very hard and brittle. They're not flexible. Anything that's flexible is not an ionic compound. And what I mean by not being flexible is that it won't bend, it will snap. So if you take a rock or a crystal and you put pressure on it, it won't actually flex like you can think of, say, a piece of rubber or a soft cover book. Okay, those can basically kind of bend, where something like a rock would not be able to. Now, the chemical properties. So chemical properties are pretty simple. They normally do not react to acids or bases. They're normally non-flammable. They do not react with oxygen or most gases. They're basically generally very, very unreactive. Okay, if you think of rocks and crystals, they've already formed a compound, so they're not going to react with many things. And they're very, very stable. And we use them for buildings, and we use them for things that we want to last a long period of time, like a granite countertop, because they don't react with very many things. Okay, so now we got this one done. We've got this one done. We got two more to go, the formation of ionics, so how they come together. So if we kind of look over here, we think, well, how does this thing come together? Is it just always one calcium and one fluorine, or is it two calciums and two fluorine? So we're going to be kind of talking about how they come together. Okay, now I know this is a big slide, so let's kind of go through this a little bit slower. Okay, so recall a bond is formed when electrons jump from one atom to another atom in order to achieve a full octet, kind of like what we have here. So see, this electron just jumped from sodium to chlorine, and now they both have a full octet. Now, during the formation of ionic bond, so the ones that we're talking about in this lecture, one atom, the metal, will donate one or more electrons to the nonmetal, causing both the metal and the nonmetal to become ions. If you remember, when we talked about elements, what ions are is when you either gain or lose electrons. Well, in the formation of ionic bond, and that's where the name ion comes from, you first form an ion, and then the ions become attracted to each other. So during this process, both atoms, the metal and the nonmetal, will achieve a stable octet. The metal losing electrons becomes a positive ion, a cation. So you can see over here, this was the metal atom, and it lost an electron, but it still had the same number of protons, so it became what we call a cation. Okay. Now, I'm going to change my color here. The nonmetal, gaining electrons, becomes negative, and the anion, I should have picked one other than green, so these are all the negative ones. Now, once you have a positive ion and a negative ion, they start bonding together as positive is attracted to negative. It's the law of opposite attraction. So positives are attracted to negatives, and you may be familiar with this with magnets. Okay, a positive side of magnets attract the negative side of a magnet. And likewise in ionic compounds. So tons of these positive and negative ions will bond together, and they form this crystal lattice. Whatever positive or negatives around, they just all basically start self-assembling into this lattice that we see here. So during the formation of an ionic compound, the elements are first, you have to be converted to an ion. An ion is just an element that has lost or gained electrons. So if we look over here, okay, we have sodium as an element. Sodium ion would be Na plus 1, because it would lose this electron, and electrons are negatively charged. I would still have the same number of protons, so it would become Na plus 1. Chlorine, on the other hand, wants to gain an electron. So an electron that's negatively charged will jump onto the chlorine, but I still have the same number of protons. So these are the ions over here, okay? And these were the elements right here. Okay. So metals tend to form positive ions called cations, as they tend to lose electrons. Okay? And if you lose electrons, you lose negative charges, and you start becoming positive. And nonmetals tend to form negative ions called anions, as they tend to gain negative charges, like I have down here. And if you're going to gain a negative charge, you yourself are going to become negative. So metals can form cations of +1, +2, +3, and sometimes +4, and nonmetals -1, -2, -3, -4. Now the number of valence electrons either lost or gained in order to achieve a full octet determines the type of ion formed. So there's a really easy way to figure out the type of ion formed. So I'm just going to kind of put a few down in here. So we're going to put oxygen, I'm going to put hydrogen, I'll put chlorine, and I'll put sodium, and I'll put calcium. Okay. Now if you want to know the what kind of ion gets formed, okay, all you have to do is my ion form is going to be oxygen 2 minus, H1 plus, chlorine 1 minus. Okay, so you can put the minus before or after. Okay, it doesn't really matter. Na plus 1, and then calcium was 2 plus. Okay. All right. Once you know the ions that were formed, and again, I'll try to do this a little bit better. This is +1, +2 column, +3 column, plus or minus 4 column, minus 3 column, -2 column, -1 column. I'm sorry, it's just really difficult to draw on an iPad. Okay, so I apologize about my penmanship. Back to show you that potassium's right here, so it forms +1, and sulfur was right here, so it formed a -2. Product table. And okay, so now once we know the ions that were formed, and that's the key thing, is figuring out what kind of ions they're going to be, then we have to use this rule, because it's not always a 1-to-1 ratio. Sometimes, like the example down here, if you look at when potassium, which is a metal, has to bond with sulfur, it doesn't bond with a 1-to-1 ratio. You actually need 2 potassiums, because sulfur only has 6 in its outer ring. 1, 2, 3, 4, 5, 6. I need 8 in order to be stable, so I need 2 potassiums, okay, each to give up an electron, and then we get when they do that, this one becomes a positive ion, negative ion, and again, I'm just, okay. In order to actually make this compound work, you actually need 2 potassiums and 1 sulfur. Okay. Now, we don't always have to basically draw them out like this. There's a much quicker way of doing it, and it's called the crisscross rule. If you remember, we did discuss this a little bit in grade 9. I'm just going to kind of back now, head here to the period. So if I go, okay. So we're going to go through basically how to form these things. So when we want to form an ionic compound, we basically take the elements that we need to use, so Ba and N, and then we have to use our periodic table and figure out, well, what kind of ions are they going to be formed. So I'm not going to keep flipping back and forth from a periodic table, but it might be handy to have one in front of you. So if we look at Ba, okay, where is Ba? Ba is in the second column. So Ba will form a 2 plus ion, and nitrogen will form a -3 ion. Okay. Well, when we want to figure out the formula, okay, instead of having to draw it out, what we have to do is we just do this crisscross. We send this 3 down to Ba, and we send this 2 down to N. So what we end up getting is Ba, 3, N, 2. You don't show the signs. So basically what happens is you just crisscross. This 2 from the Ba goes and attaches to the N at the bottom, and the 3 from the N goes to the Ba, and it has to be at the bottom. It has to be written just like I wrote it here. Okay, so if you look at Be and Cl, well, I know that Cl is 1 minus. And then if I look at my periodic table, I know that Be is 2 plus. If I do my crisscross, this 1's going to come down here, this 2's going to come down there, and I would get Be 1 Cl2. Now notice, sometimes you don't include that 1. Sometimes they'll just write Be. If there's not a number there, then you can assume it's 1. So this formula is BeCl2. Look at lithium. Lithium is 1 plus. Iodine is 1 minus, or -1. If you do the crisscross, you get Li I, and 1 and 1. Or sometimes I'll just leave it as Li, I. Okay. If we look at Sr, so Sr is 2 plus. Phosphorus is minus 3. If we did the crisscross, I would get Sr3, P2. Okay. Last one, Rb and O. So rubidium is 1 plus. Oxygen is 2 minus. So I would get Rb2, O1, or sometimes I would just leave the 1 off. Okay. So it's very important when we do ionic formula compound formation that we always use table right here. And basically you kind of look and you say, okay, everything in this column forms a plus. Sorry, I'm just trying to write in here. Everything in this corner forms a plus 1. Everything in this column a plus 2. Skip over the middle. Everything in this column a plus 3. This is plus or negative 4. Everything in this column is minus 3, minus 2, minus 1. And then nothing in this column because they don't form compounds. So I think some of the examples I had was I had hydrogen. Well, that's going to form a plus 1 because it's in this column, and everything in this column will form a plus 1. So I think I also had sodium. So sodium will also be plus 1. I think I had calcium in there, and calcium is right here. So it's in this column, so it will form a plus 2. I think I threw oxygen in there, so that's going to form a minus 2. And then chlorine is in this column right here, so it will form a minus 1. Crisscross rule. Okay, the last one is naming. So this is the last kind of thing we're going to go through, the last slide. So ionic compounds have a very simple naming system as well. Basically, you always name the metal first as it appears on the periodic table. So you just look at the metal that's inside here. So I'm just going to highlight all the metals. So there's the metal, 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 metal. Here's my nonmetals in red. Okay, now, because you had to use the crisscross rule, the nice thing is you never have to worry about any of these numbers. You never have to, you just basically just kind of write out the name, just like I have here. So you name the metal first as it appears on the periodic table. So this is sodium. Okay. Then you name the nonmetal, dropping the ending of the nonmetal and adding "ide." So instead of chlorine, it's going to be chloride. So this would be sodium chloride. You'd almost do this naturally. Most people do this naturally where you wouldn't just name it as sodium chlorine because it sounds weird. You just automatically start switching it. So let's go to our next one. Name the metal as it appears. Calcium. Okay. Normally it's fluorine, but we drop the ending and it's going to be fluoride. Aluminum. And then normally it would be oxygen, but we drop the end, and aluminum oxide. This will be lithium. And then normally chlorine, but we drop the ending, chloride. Okay. So I hope this helps. We'll do a little learning check for ionic compounds, and then next week, covalent compounds.